So hello everyone. The topic and the problem questions I will be covering will be hydrologic mass balance, or also called as water budget equation. So the theory, uh, just little bit theory on this topic, and then we will move to the additional questions. The theory part we have covered in class also. So, but I will be briefly touching upon it again. So the topics for this presentation is hydrologic budget or balance equation, and we will have three examples based on this equation. So the hydrologic budget or water balance is a measurement of continuity of the flow of water, um, which holds true for any time interval and applies to any size area. And it can be a small area, it can be big area, or it can be earth as a whole. So the continuity equation we use to measure flow of water, and this continuity equation we had derived from Reynolds transport theorem, which we studied in fluid mechanics, and which the basis for using this theorem is because we want to analyze uh, with respect to control volume instead of the systems approach. So, so it's just where it is coming from. Now, for establishing the hydrologic budget equation, the continuity equation of water can be written as mass inflow minus mass outflow is change in mass storage. And if the density of inflow, outflow, and storage volume is the same, in our case, it is storm water runoff. So we can rewrite the equation of mass inflow minus mass outflow is equal to change in mass storage as VI minus V naught is equal to delta S. And what would be VI? VI will be inflow volume of water into the problem area during the time period. And VO subscript is outflow volume of water from the problem area during the time period. So outflow would be, right? So I think we got that. So it is outflow volume from the uh, area. So if I am considering this as my detention pond, I have VI coming in, VO going out. Okay. And what is delta S? It's change in mass storage, change in now it's not in mass storage because we are expressing in terms of volume. So we will be writing it as change in storage of the water volume over and under the given area during the given period, given time period. Okay, so that is your equation. Now, what would be the units of this equation? So please read this carefully. In hydrologic calculations, rainfall, evaporation, and often runoff volumes are expressed as average depths over the catchment area. So when they are expressed as average depths, it means they are expressed either centimeter, inches, feet, etc. Now further, the equation you just saw, hydrologic budget equation or water budget equation, it can be expressed separately for the surface water system, groundwater system, and as a system equation. By system equation, I mean surface water plus groundwater together. So this is your SW and your GW together as a system equation. So now again we are talking about units. Volume per unit time separately. So it can be expressed as volume per unit time. Your surface water system or groundwater system or system equation can be expressed as volume per unit time, which is nothing but meter cube volume per unit time, which is flow rate. Or if your time period is given, which is delta T, and area is given, which is A. Area can be given in meter square, kilometer square, hectare, etc. Then if it is given in time period is given, area is given, you can express it in depth. So you can express it in depth. Okay. So these are the units, and in the problems you will see that too. Now the surface water equation, surface water system hydrologic budget equation. So first is the water budget equation just for surface water system. So means the water which is on the ground. So whatever water is on the ground, we will quantify that. So we will see here, we have the precipitation. We will be reading this equation plus the diagram. So we have the precipitation on falling on the ground. We have the precipitation P. We have the inflow Q in, which is in your surface flow into the system, which can be stream, and Q out will be surface flow out of the system. So here you can see there is a stream inflow here. Here is showing the stream outflow. Okay, Q out is right here. Then we have QG, which is the groundwater flow into the system. Groundwater flow into the system. And EG is your evaporation. TS is your transpiration. I is your infiltration. So here it is shown here, ES, TS. So right now we are talking about surface water. So we are not talking about G here, because G subscript is groundwater and S subscript is, so if it is written ES, so S subscript is surface water, right? So ES is subscript is surface water, that is equal to change in storage. So all the parameters are explained here also. So this is the surface water equation. Now your groundwater system equation. So you have infiltration, because infiltration is for groundwater recharge. So here it is showing infiltration. And you have G in, which is groundwater flow into the system, groundwater flow out the system. So it is shown here. So QG is the groundwater flow into the streams, which we saw that in the previous equation. So that was QG. That's why it is negative sign. Evaporation from groundwater, transpiration from groundwater is change in storage in groundwater. So that is your groundwater system. Now, if you add both of them together, you will get your system hydrologic budget equation. You understand all these terms and they can be written as P precipitation, Q is runoff, E is evaporation, G is groundwater, T is transpiration, which is equal to delta S. So you can see here SS is for surface water, subscript is small s, subscript is small g, this is for ground. So this is your final equation for, you can use based on what the problem is, we can use surface water equation if there is no um, influence of groundwater in your problem, or either way, right? So now this equation can be further written as P minus Q minus G plus E plus T is equal to delta S, which can be also labeled as losses. So L will be G plus E plus T, which is losses. So whatever is the runoff, we are quantifying that, and whatever goes to the subsurface system, we are quantifying that as losses. So this is your brief theory about your hydrologic budget equation. So let's, okay. So before we move now, next is why we need this hydrologic budget equation. What is the purpose of it? So it's given idea about water resources availability and its use in various sector. So we can use balance equation for hydrologic modeling and simulation, estimation of unknown variable like evapotranspiration, our precipitation and runoff simulation, water utilization exercise, how much is being utilized, and estimation of how much do we have, how much do we need, how much is the gap, water resources planning, and pre-feasibility studies of interlinking projects. So, for example, I have a Rio Grande River and I consider water supply to my home from the river. So I have a development here, development one, I have development two, and we are getting our water, which is water resource for us, right? Now there is a huge development coming three. So we need to see pre-feasibility studies. I have a population addition on this lot, three, which was not there, and I want to borrow water from Rio Grande for water supply. So I need to do pre-feasibility studies for interlinking projects. So this is can be kind of example you are looking for in this one. So with that, let's look at the um, additional example. So let's read the statement. So statement says, so statement says that we have, statement says that we have a um, catchment area of just catchment area of 150 hectare. Let's just reading the statement. So this is given to us. and we have a rainfall of 10.5 centimeter in 90 minutes due to a storm at the outlet of the catchment. So I have my catchment, right? So at the outlet of the catchment, so this is my outlet of the catchment. The stream draining the catchment, so I have a stream which is draining the catchment. So all the water from the catchment is flowing at the outlet through this stream. This is the direction of flow. So was dry before the storm. So stream draining was dry. There was no flow and so there was no flow in it and experienced a runoff lasting for 10 hours. So runoff is with an average discharge value of 2 meter cube per second, and the runoff lasted for 10 hours. So the stream was again dry after the runoff event. After 10 hours, there was no runoff at all. What is the amount of water which was not available to the runoff? So from slide 7, I just mentioned that P minus R minus G minus E minus T is equal to delta S, my hydrologic budget equation. Whatever is not available to the runoff, that is G plus E plus T, because this is not available. This part of budget equation is not available to the runoff, right? So it means I can say I need to calculate, therefore I need to calculate losses, which is equal to L is equal to G plus E plus T. Therefore, I can rewrite my equation as P minus R minus L is equal to delta S. I can also see from the statement that the stream was dry before the rain started, and after 10 hours, after runoff was over, stream was again dry. So it means I can also conclude from the given statement that delta S is equal to 0. So therefore, P minus R minus L is equal to 0. Therefore, here I can write it as given. Therefore, P minus R is equal to L. So this is my equation 1. So this is my equation. Now I need to solve for L. So that is my first part. What is the amount of water which was not available to run off due to combined effect of infiltration, evaporation, and transpiration? So infiltration led to groundwater. Okay. Okay. So now let's see what was the given value of P. So P was given to us as P is given to us as, we have already written there given. Now we know the units can be either in volume or it can be in depth. We already know that, right? So let's see. So P is equal to 10.5 centimeter. R is given to meter cube per second. So either you convert R to centimeter or you convert P to meter cube. Okay, so let's convert R to centimeter. So 2 meter cube per second is equal to 2 meter cube multiply by the area given to you is 150 hectare. So that is divided by area. So this is area of watershed. So you divided it by that. So this is giving you in meters already, but we have seconds also. So those seconds, we know the runoff existed for 10 hours. So we will be doing 10 hours. So we have 10 hours. And what is 1 hour? 1 hour is 60 minutes divided by hour, multiply by 60 seconds in minutes, right? So it means I can cancel this out. Hour cancelled with hour, minute cancelled with minute. Second, because here it was second, I did not write here. So second got cancelled with second. So now R is 2 divided by 150 into 10 raised to power 4 into 10 into 60 into 60 meters, because meter is left. So R, after calculating all this, I am getting that as 0.048 meters, which is equal to 4.8 centimeters. So I got P, I got R. So from equation 1, I have P is 10.5 minus 4.8, I am getting as 5.7 centimeter. So therefore, I can write from the equation that amount of water not available to the processes, amount of water not available to evaporation, infiltration, and transpiration is equal to 5.7 centimeter. What if I will ask you the value? Here in the question I have not asked you, but if I will ask you the same value in meter cube, so this will become 5.7 centimeter into 1 by 100 centimeter in meters into 150 into 10 raised to power 4 meter square. So centimeter cancel, I am getting these L value. So I should write here L, therefore, this L becomes equal to 85500 meter cube. Okay, so this was part A problem, right? Part A of the problem. So this is part A solution. This is part A solution. Now, second part of the problem is, B part of the problem is calculate runoff to precipitation. So you can easily calculate, you have both the values, runoff to precipitation value. So you have both the values, runoff you have calculated as 4.8, precipitation is 10.5. So your answer is just a second, let me calculate. So it is 0.8 divided by 10.5. So you are getting 0.457. So this is the complete solution of your problem. Okay. So let's go to the next question. So next question you have again the hydrologic budget equation, and you are calculating for evaporation losses. So let's see what is given to us. So reservoir area is given. Use the following data to compute the annual evaporation loss in MCM, which is million cubic meter. And in a year of 365 days. So delta T is given to me as 365 days. Time period. So reservoir area is given. Contributing rainfall is given. Mean annual inflow is given. I am writing QI because it is liter per second. Mean annual outflow is given. And increase in storage is given, which is given as a positive sign. It means there was addition in the storage, which means there is a positive change in depth of your reservoir. Okay. So what we mean, so this is my reservoir depth. Now there is, we are just saying there is increase of this much volume. So which is 2.5 MCM. Positive increase, right? So this is at T equal to 0. This is at T equal to 365 days. Okay, so that's what the problem means, right? So now let's use the hydrologic budget equation to calculate your evaporation loss. Now, in this case, you have no mention of groundwater, but still we will be using the equation of the system to calculate our evaporation loss. So step 1, I will have as using my system hydrologic budget equation, I can write it as P minus Q out minus Q in minus ES plus EG. It is from the previous slide. So TS plus TG, you know, I am writing both the subscript. So though both the subscript are for S and G, we know are surface water and groundwater. So this is your equation. Now we don't have any groundwater. We have not been mention of any transpiration. So we will take this out. We will take the groundwater out. So what we are left with, P is given to us as 1800 mm per year. Q out is given to us as 110 minus 130 liter per second. Evaporation we need to calculate. And delta S surface plus groundwater, we have been given a positive increase of 2.5 into 10 raised to power 6 meter cube. Okay. So this is now rewrite this equation ES plus EG, or we will write it as E is equal to 180 mm per year minus 20 liter per second minus 2.5 into 10 raised to power 6 meter cube. I am writing all the units Why? Because your units are different. We can't add the numbers of different units. We need to bring the units in the same system and in the same unit. So we will be converting all, so I should write here 1800. So we will be converting all this into meter cube. So 1800 mm divided by 1000 mm into meter, right? Multiply by area, which is so the area given to us is 250 hectare. So which will be 250 into 10 raised to power 4, right? Plus, now so it becomes plus, right? 20 liter per second. So 20 divided by 1000, I will have liter into meter cube per second. So because I am calculating it on an annual basis, so I need to convert per second. So this is per second. So I am converting this second into year. So this will be 365 days in a year multiplied by 24 multiplied by 60 multiplied by 60 seconds in 1 year. So this is my second term, 20 liter per second. This is my second term. Now, third term is, so I got this per year, meter cube per year got cancelled, second in 1 year. This I have as meter cube. So I should have written here meter square. So meter square, so it becomes meter cube because this will cancel out. So I have little cancel out, second cancel out. I'm left with meter cube per year. Now the third term is 2.5 meter cube. So this is already annual. So no change is required in this one. So here I am writing this as 450 into 10 raised to power 4 plus 630720 minus 2.5 into 10 raised to power 6. So solving this, I got 450 10 raised to power 4 plus 630720 into 10 raised to power 4 minus 250 into 10 raised to power 4. So all is, even though putting in the calculator, you will get the answer. So I am getting 263.072 into 10 raised to power 4 meter cube, which is equal to 2.63072 into 10 raised to power 6 meter cube, which can be written as 2.631 million cubic meter, because my answer needs to be in million cubic meter. Okay, so this is my next problem. Now the last problem for this hydrologic budget is this one. So let's see what is given to us. So we have been given 2 centimeter of water evaporated. So we have been given evaporation 2 centimeter from 150 hectare vertical walled reservoir. So this is my reservoir, area is 1 during, what is the time period given? 24 hours. Storm water was added, Q in, at a constant rate of, and there is evaporation, E, at a rate of 2.5 meter cube per second. Determine the volume of water released in hectare meter during the, so from the bottom of the reservoir, so from the bottom of the reservoir, volume was released, VO. We want to calculate that during the period of 24 hours. We don't know. And the water level did not change. It was same at the beginning and the end of the day, which is delta T, 24 hours of a day. Also determine the average outflow rate from the reservoir. So it is saying A, calculate V naught, B, calculate Q out or QO. That's how we are writing it. So QO. Okay, so this is not. So this is not known. We need to calculate that. So we are saying delta S is equal to 0. So there is no change in delta S. Okay. So we already, so based on what we know, we will again write our equation. So our equation would be P minus, so we will again write the step 1 would be, we will write the budget equation, which will be P minus Q out minus Q in minus ES plus EG. There is no mention of groundwater because it's a reservoir. It's a vertical walled reservoir. So there is no mention of groundwater, no mention of transpiration. So G out minus G in is equal to delta SS plus SG. So based on this, we can say evaporation is there, transpiration is out, groundwater is out, and we have no change in storage. So what is my final equation? P minus Q out minus Q in is equal to 0. So from here, we can so we have, sorry, we have the precipitation too. So we need to account for that. We have the evaporation too. ES plus EG is equal to 0. So based on the data given, we just have been given, there is so when the storm water is being added, this can be a moment when there was no runoff. There is just the runoff. So we can just take the precipitation out from this event. So precipitation is also out because that's not given to us in the problem. So what is now my, so this becomes minus, what is your Q out that we need to calculate? Q in is given to us as 2.5 meter cube per second minus your E is given to us as 2 centimeter is equal to 0. So let's now calculate what is given to us. So QO is minus QO plus 2.5 minus, sorry, we need to keep the units with us. So this is meter cube per second. Meter cube per second minus 2 centimeter is equal to 0. So Q naught in meter cube per second, we are writing it as 2 centimeter minus plus 2.5 meter cube per second, right? So we are keeping this as same. So now so we are getting the Q naught meter cube per second, which is minus 2. And what is the area given to you? Area is given to you as, so let us first see that we need to calculate the flow rate also. So we will be calculating it in meter cube per second. So 2 centimeter divided by 100 centimeter into meter is my multiply by area is given to me as 150 hectare, which is 150 into 10 raised to power 4 meter square. And what is the time period given here? Time period is 24 hours. So over 24 hours. So we have 24 into 60 into 60 seconds plus 2.5 meter cube per second. So our Q naught in meter cube per second. So let's calculate that. We have so let's cancel this one out. So 2, so this is out. So we are left with now 2 multiplied by 150 divided by 24 divided by 36. So we are getting this as minus 0.347 centimeter out, centimeter out. So we got meter cube per second, right? Plus 2.5. So this is our Q naught. So we got 2.5 minus 0.347. So we got this as 2.153 meter cube per second is our outflow. So that is outflow at the end of the day. Now, what is the water level in the reservoir was the same, but we had to calculate volume of water released in hectare meter. So volume of water released in hectare meter. So VO in hectare meter. So you will be calculating 1.5. So 2.153 meter cube. So I will be meter square into meter per second. So this is 2.153 in divided by 10 raised to power 4 meter square, hectare, meter square, and you need to calculate it in hectare meter. So we will be again multiplying it with 24 into 60 into 60 seconds divided by seconds. So what we are left with, let's see. So we have meter square got cancelled. So we had 1 meter, I should show here. So 1 meter was left and this second got cancelled, right? So you got now VO in hectare meter as 2.153 divided 10 raised to power 4 into 24 into 60 into 60. So this is your answer in hectare meter. So 2.153 multiplied by 24 multiplied by 60 multiplied by 60 divided by 10 raised to power 4 gives you 18.6 hectare meter as your answer. Okay, so that is about it for your water budget extra problems. Thank you, and I'll see you in next set of practice questions.